Welcome to the BME 244 Statistics module. My name is Matthew Novak and I'll be your instructor throughout the length of this online course. The beginning lecture I want to give is basically just an introduction to statistics. And before going over any specific concepts in detail, I basically want to ask the question of what are statistics and what kind of questions do they answer that will be useful for you as engineers. Well, the first and most obvious is it answers the question of how do we describe and present data in a way that is most instructive for you as a researcher and an engineer. Secondly, it answers the question of how do we interpret and understand our data, and this is what's called descriptive statistics. And lastly, it allows you to draw certain conclusions and judgments from a set of data that can help you further with further experiments, and this is called inferential statistics. And through the length of this course, the goal is to cover all of these to make you well versed in the field of statistics. So the first concept we're going to discuss is the idea of distributions. And I'm going to begin with the definition of a random variable. And much like the name implies, a random variable is a variable whose value is subject to random chance. And for the length of this course, we'll be defining that as a big X. Unlike other mathematical variables that you've probably encountered, a random variable doesn't have one fixed value. Instead, a random variable can take on a range of different values with each value having an associated probability. So for example, one such example would be the last digit of a person's social security number. It could be anywhere between 0 and 9 with associated probabilities for each one of those numbers. We're going to go over a specific example in this section where we're going to look at the heights of students in a classroom of 20 kids. And so what we'll do is we survey the classroom, take heights from all of them, and then we make bar graphs of the different heights for different groups of people. So you can see here between 5 feet and 5'5", between 5'6" and 5'11". Each one of them, the y-axis is just how many occur in that grouping. So for between 5 feet and 5'5", there are 2 kids. Between 5'6" and 5'11", there's 13, so on and so forth. Now, if we were to divide the totals in each one of these bins here by the total number of 20, our y-axis would change, and it basically, instead of going from 0 to 20, now the y-axis would go from 0 to 1, or in this case 0.7 because we cut it off. But this is the percentage of students now that are within this specific grouping. And so this is actually a distribution. This shows how the heights in the classroom are distributed among these 5 groupings. And what's important to note is that all of these bars here have to add up to 1. So, which intuitively should make sense because they all have to add up to the total number of students in the class. And so this actual distribution here or this plot is what's called a probability density function. And so what that means in layman's terms is just the odds of drawing a student from these specific values along the x-axis. And so moving forward, we can use these probability density functions and distributions to describe random variables. So having our same probability density function, or PDF, as before, we can ask the question, for example, what are the odds that a person drawn at random from the class is either 6 feet or taller? So just by inspection, you can look and see 6 feet or taller would be the bar for 6 feet to 6'5" inches, 6'6" to 6'11", and 7 feet. So it's these bars on the right that have been highlighted yellow. And so basically, to find the odds, you just sum up the probabilities of each one of these. So for 6 feet to 6'5", it's about 0.27 is the y-axis value, and for here it's about 0.01. So it adds up to 0.2808. So what that means is you have a 28% chance, roughly, that a person drawn at random from the class is 6 feet or taller. If we were to look at this, put this in more mathematical notation, if this were a curve instead of a collection of bar graphs, what we could do is integrate, or take the area under the curve starting at 6 feet and going towards infinity, because it's anything taller than 6 feet of the distribution we have. And more generally, if we wanted to find the probability between any two numbers, it's basically just the area under the curve of the probability distribution function. So for example, if I wanted to find the probability of people between 5'6" and 6'5", I would integrate starting at 5'6" and go to 6'5". So 5'6" would be the lower bound of the integration, and 6'5" would be the upper bound. So this brings us to the idea of descriptive statistics. So what kind of values can we use to describe this set of data that we have here? Well, the first and most obvious that I'm sure everyone is aware of is the idea of the mean, which is basically the sum of all the data points divided by the total number of data points that you have. It's a measure of what's called the central tendency, or what's most likely to occur. So just by looking at this graph here, if you were just looking at it by inspection, you would say that the central tendency is that students would be between 5'6" and 5'11", so this bar right here. So if you just had to guess, I would imagine that the mean height would be somewhere between 5'6" and 5'11". Another way to describe the data is the variance. So it's asking the question of how far are the data points from the mean. Data set with a very small variance would have most of the data points clustered around this mean value, whereas a data set with a large variance would have much more a spread look to the data. And also there's the standard deviation, which for right now we'll just define as the square root of the variance. This brings us to the concept of random sampling. And with random sampling, the definitions of those means and variances change between what's known as a population and what's known as a sample. So we'll get into that here. First, we're going to define a population as the total set of observations that can be made in a particular study. So we'll define that as big N. Within that population, you can draw what's also called a sample, which is just a set of observations that are drawn from a population set, which we'll define as little n. And as mentioned before, the definitions of variance and standard deviation change between a population and a sample. And that's something worth noting when you're going to be doing calculations for experiments in the future. So this is a little table that was built to try to describe that. And so for a data set with I values and a population size of big N and a sample size of little n, we're going to show you how the definitions for mean, variance, and standard deviation change. So for population, the mean value is as you would expect. You sum all the values x and just divide by big N. And for a sample, all that's changing is instead of, if I draw a sample of 10 numbers, what I do is I sum up those 10 numbers and then just divide by 10, which is our little n in this case. So for the variance of a population, you can see this is the equation here, and it looks a little complicated, but when you think about what the definition of a variance is, it's how far is a data point deviate from the mean. And you can actually see this borne out in the numerator of this equation right here. If I have a value x sub I how far is it from the mean? What's the difference between those values? And since you can't have a negative variance, you square the value and just divide by big N. Now for sample variance, it's pretty much the same thing. Instead you're dividing by, or you're looking at the difference between a point xi and the sample mean instead of the population mean. But instead of dividing by big N, you're dividing by little n minus 1, which is what's called a non-biased operator. It's not important for the sake of the discussion here, but it's worth noting that instead of dividing by little n, it's little n minus 1. And furthermore, the standard deviation of a population is just the square root of the population variance, and the sample standard deviation is just the square root of the sample variance.